Hey there folks, welcome to the next episode of Physics Theory. I'm your host, Rev Bari, Brown University physics grad student. Today I'm going to be solving a problem about thermodynamics. In particular, I'm going to be solving for the partition function for a simple harmonic oscillator. So let's just do a brief recap. What is the simple harmonic oscillator and what are its energy levels? So let's take a look. The simple harmonic oscillator is just a spring. So here is a simple harmonic oscillator. And it's described by a very simple Hamiltonian. The Hamiltonian describing the simple harmonic oscillator is just a kinetic energy, E squared, divided by 2m, which is the same thing as 1/2 mv squared, plus 1/2 m omega squared x squared. This is just another way to write the spring potential, which is 1/2 kx squared. It's the same thing. Now, the next question you should ask yourself is, wait, what are the energy levels given the Hamiltonian? Well, to answer that question, you need the Schrödinger equation. In particular, the time-independent Schrödinger equation will give you the stationary states of your system. The stationary states are the states that have an average expectation value of 0 for the position, momentum, velocity, and acceleration of the system. So, given all of that, let's go ahead and find the energy eigenvalues of our harmonic oscillator. So we can rewrite our Hamiltonian here in a way that helps us find the energy eigenvalues. We can rewrite this messy Hamiltonian as simply the number operator n plus 1/2 times h bar omega. The benefit of doing this is that now we can rewrite psi sub n, the nth eigenstate, in ket notation as ket n, and likewise ket n here. And now we can rewrite the Hamiltonian as n plus 1/2 h bar omega, where n is the number operator. Now, when the number operator acts on the nth eigenstate, it just gives you back n. That's what the job of the number operator is. If n acts on n, it gives you n. I mean, it doesn't get much more straightforward than that. So that means the energy eigenvalues here are going to simply be n plus 1/2 h bar omega times ket n. So the energy eigenvalues, we can just read them off. This is the energy value of the nth eigenstate of the simple harmonic oscillator, n plus 1/2 h bar omega. So now that we've figured out the energy eigenvalues of the simple harmonic oscillator, we can calculate the partition function of the simple harmonic oscillator. So let's do that. Remember, the partition function z is simply the sum of all the Boltzmann factors of a system, where the Boltzmann factors are simply these exponentials that sum over the energy states of a system. Now, we already know what the energy states of our simple harmonic oscillator are. It's simply n plus 1/2 h bar omega. So let me erase this and write that down. So that z, the partition function, is the sum over s of e to the minus beta n plus 1/2 h bar omega. But wait a second, now I can simplify this further. I can take out this constant 1/2 h bar omega so that z, the partition function, is e to the minus 1/2 h bar omega divided by kt from that beta times the summation of e to the minus n h bar omega over kt. Now this over here on the right side is no more than a geometric series. But I know how to add geometric series. A geometric series like 1 plus r squared plus r cubed, let's call the sum of that s. Well, that sum is simply the first series term, a naught, divided by 1 minus r. That's the sum of a geometric series. So we simply take the first term in this geometric series, which will be 1 because it starts from s equals 0, or actually I should use n instead of s now because I'm summing over those n states, divided by 1 minus, what is my geometric ratio? It's simply e to the, be careful, e to the minus h bar over kt, not n h bar over kt, because you multiply each factor, each additional term, by e to the minus h bar beta, h bar omega beta, but that n doesn't come into play. And I multiply all of this by e to the minus 1/2 h bar omega beta. And that, ladies and gentlemen, gives me the partition function for the simple harmonic oscillator. Now that you have the partition function, you can do anything you want using it. you can calculate the energy of the simple harmonic oscillator simply using minus partial beta of the natural log of z. You can calculate the entropy of the simple harmonic oscillator system using the average energy divided by T plus K ln Z. You could find the pressure of the simple harmonic oscillator by doing minus partial F partial V, where V is the volume of the system. What is F? F is the Helmholtz free energy. F, which is the connection between thermodynamics and statistical mechanics. F is minus KT ln Z. So as soon as you have your partition function, you immediately know the free energy, the entropy, the pressure, the energy, any thermodynamic quantity you want is now in your hands. So that is how you calculate, how you derive the partition function for the simple harmonic oscillator. Thank you for watching this episode.